Okay, welcome back. We'll take a look at pages 5 and 6, radian angle measurement. Okay, radian angles. They show up a lot, again, in pre-calc and calculus, so we want to get a sense of what radian angles are. Radians are just a different way of measuring an angle. So let's take a look. Just as distance can be measured in feet or inches or miles or centimeters or whatever, right? Lots of different ways to measure distance. Rotations about a point can also be measured in different ways. Measuring one complete rotation in terms of 360 degrees is somewhat arbitrary. A common unit of angle measurement that is an alternative to degrees is called the radian. You first saw this unit of angle in Common Core geometry. It is natural to define it in terms of a geometry of a circle given the unit we are in. Okay, so again, basically a radian is just going to be a different way of measuring an angle. We have degrees, which we're used to. You've worked with those a lot over the years in math. Now we're talking about a different way. So let's see what this is all about here. The definition of a radian. The radian angle theta, created by a rotation about a point A using a radius of r and passing through an arc length of s, is defined as theta equals s over r. Okay, so what are they talking about here? Well, let's take a look. Okay, the diagram's okay, I guess. But in general, look, let's suppose I have a circle centered at the origin, okay? And I measure some angle. I'm going to call that theta, okay? So I'm going to start here, and here I measure up somewhere in the first quadrant. There's my angle theta, that guy right there, okay? Now, if you think about it, this length is basically the radius of the circle, right? We have this circle centered at the origin. These segments represent the radius. Here's the angle I measured around the center of the circle. This is called the arc length, which they're labeling with the letter S. Okay, that's what's going on here. So, this is just a portion of an entire circle that they're trying to show us. Okay, so there's the bigger picture, if you will. All right, so imagine we have some angle centered at the origin, and here's the length of the radius of this circle, and it creates this arc. All right, so the size of the angle will directly affect the size of that arc. Right, if I make a bigger angle, I'd have a much larger arc. All right. Start here, and now I go into quadrant 2, right? Obviously, I have a much larger arc. That would be S. Here's my angle theta, and still these segments represent the radius of the circle. Okay, so there's certainly a relationship between the size of the angle and the size of the arc that's intercepted, okay? And that's what this formula represents, okay? And basically, the definition of a radian is basically what we're calling this angle theta here is basically the ratio, right? It's S over R. That's a ratio. So we basically look at how long is this arc, and we divide it by the length of the radius. That's how we define a radian measure. Okay, so it's completely dependent on the size of the angle, the size of the arc, and the length of R. Okay, so in any event, that's the idea. That's the definition of a radian. It's the ratio of the arc length to the radius of the circle. And if we do a little bit of algebra on this formula, we could actually multiply both sides by r to get it out of the denominator. And that's what gives us that formula, S equals theta times r. Or I usually write it as S equals r theta. Either way. Okay. But again, basic idea of a radian, if we have a circle, okay, we have a circle. I measure some angle. Okay, so I have this big angle here. That's theta. Okay, whatever the length of this is, r. Here's my big ol' arc length this time. Okay, whatever this angle is just going to be whatever S is divided by r, and we call that a radian measure. Okay, so let's take a look and get a sense of how radians are going to be tied into the circle that we talked about in the last lesson with like 60 degrees, or excuse me, 90 degrees, 180, 270, 360. Okay, so let's take a look at this exercise. Consider a full rotation around any point in a counterclockwise positive direction. Okay, you have a full circle. Okay, entire rotation about a point. So we've got a full circle, okay? What is the arc length S in terms of the radius of the circle R? Okay, well, here's the radius of the circle, okay? Now, the arc length would be the entire distance around the circle this time because we measured all the way around. All right, well, what do we call all the way around the outside of a circle? That's called the circumference, and that's what arc length represents here, okay? So the arc length S is actually the circumference. Well, what's the formula for circumference of a circle from geometry last year? 2 pi r. Okay, so that's our arc length if we were to measure an entire way around a circle. Great, we have an angle that goes all the way around the circle. In other words, we have a 360-degree angle. Okay, the arc length would be 2 pi r, full circumference. Now, part B, based on the definition above and on your answer to part A, how many radians are there in one full rotation? Well, again, in terms of degrees, a full rotation is 360 degrees. Let's see in terms of radians what a full rotation is. So again, the formula is S equals R theta. I'm using this formula from above. That's typically the form of the formula I use. Now, we just figured out that S was the full circumference of the circle, which we're going to write as 2 pi r. And that's going to equal R times theta. Now, we want to know how many radians there are, so we're solving for theta. So, solving for theta, let's divide both sides by r to get theta by itself. And what do you notice we're left with? 2 pi equals theta. What this means is that the full way around a circle in terms of radians is 2 pi radians. There's 0 radians, and if I measure all the way around this thing, a full circle, I get back to where I started, that's 2 pi radians. Okay, so 2 pi radians is the full rotation of a circle. 360 is the full rotation in degrees. 2 pi is the full rotation in radians. Radians essentially measure the total number of radii, hence the name, that have been traversed about the circumference of a circle in a given rotation. Based on the circumference formula of a circle, thus, there will always be 2 pi radians in one full rotation. Okay, use the formula above to answer each of the following. Determine the number of radians that the minute hand of a clock passes through if it has a length of 5 inches and its tip travels a total distance of 13 inches. Okay, so let's try to envision this. Now, we've got our clock. Okay, and determine the number of radians that the minute hand of the clock passes if it has a length of 5. So here's my minute hand, okay? That's going to be 5. That's basically what part of the clock it looks like, or what part of the circle? The radius, right? And the tip travels a total distance of 13 inches. So this thing's going to travel around here. This is the tip of it, and it's traveling a total of 13 inches. Okay, so maybe something like that, and then that's where the thing ends up. Okay, so we started over here, and we traveled 13 inches and ended up there. Okay, here's our angle theta. The 5 is the radius. The 13 is the S. S equals R theta. Okay, we traveled 13 inches around the arc. The radius will be 5, and we're solving for theta. So dividing by 5, we get 13 over 5 radians. Or if you want to clean that up a little bit, I want to say 2.6 radians. Now, what exactly does that mean? All that means is like 2.6 radians is the angle that got created such that this distance ended up being exactly 2.6 times the length of the radius. Okay? An angle that's created with an arc length of 2.6 times the radius is that angle. That's what we call a radian. Okay? Part B. If a pendulum swings through an angle of 0.55 radians, what distance does its tip travel if it has a length of 8 feet? So picture a pendulum, right? This thing swings back and forth. All right. Well, if you think of it, that's basically a portion of a circle. We could think of the pendulum itself as the radius. Here's the angle that gets created as it swings back and forth. and this portion of it is our arc length. So it swings to an angle of 0.55 radians, so that's theta. What distance does its tip travel that has a length of 8 feet? So the length of the pendulum, the radius is 8 feet. We're looking for the arc length this time. S equals r theta. S is going to be 8 times 0.55. And so let's see what that ends up being. 4.4 feet. Okay, so if we had a pendulum that was 8 feet long and it swings a little more than half a radian, it's going to cover 4.4 feet. All right, folks, so a couple S equals R theta problems. Let's turn to the next page. Radians are essential in the study of higher level math, as I said earlier, in physics, and are the angle measure of choice for the study of calculus. It is important to be able to convert between angular system of degrees and that of radians, right? We can convert between feet and meters. We can convert between any units of measure. We can convert between angles and radians. There's a relationship between the two. Okay, exercise 3. Consider 1/2 of a full rotation. What is the angle of rotation in both degrees and in radians? All right, so again, in degrees, we go all the way around, that's 360. In radians, we go all the way around, and that's 2 pi. So it looks like 2 pi and 360 are all the way around. Well, what's halfway around in degrees? That would be 180. What would halfway around in terms of radians be? Well, if 2 pi is all the way around, half of that would be 1 pi. So halfway around the circle is a measure of pi radians, okay? But the key here is that these are equivalent. 180 degrees is equal to pi radians. Those are the same, just like 360 degrees is equal to 2 pi radians. Just like 12 inches is equal to 1 foot, okay? These things are equivalent, okay? Part B, using the two equivalent angles of rotation in part A, convert a 30-degree angle into equivalent angle in radians. Well, look, if we have 180 degrees, what do we have to divide that by to get to 30 degrees? Well, let's divide by 6. That'll take us to 30 degrees. So if I start with the equivalent radians, which is pi, and I divide that by 6, I would write that as pi over 6 radians. So 30 degrees and pi over 6 radians are the same. Okay, so there's a more formalized way to convert between degrees and radians, and that's what we're going to talk about here. So in exercise 4, convert each of the following angles and degrees into radians. Here's how it works. To convert from degrees to radians, you take your degree measure, and because pi and 180 are the same, pi radians and 180 degrees are equal. Okay, it's going to look a little weird, but what I'm going to do is I'm actually going to take my degree measure and I'm going to multiply it by pi radians over 180 degrees. And what's going to happen is my degree units are going to cancel out, okay, and I'm going to be left with something in terms of radians. Okay, so let's see how this works. Convert 90 degrees into radians. I take 90 degrees and I multiply it by pi radians over 180 degrees. The degree units are going to cancel. I'm going to get 90 pi over 180. Right? You can think of that as 90 over 1. Multiply tops, multiply bottoms. Now simplify. 90 over 180 is 1/2. So this simplifies to pi over 2 radians. Okay? And the next example. 120 degrees times pi radians over 120 degrees. The degree units cancel. I get 120 pi over 180. And if I simplify 120 over 180, the easiest way to do that is write on your calculator, use your math fraction. We get 2 over 3. Now, don't lose sight of the fact that we have a pi in our numerator, so this becomes 2 pi over 3 radians. Okay, and in part C, we're going to take 225 degrees and multiply by pi radians over 180 degrees. Those units cancel. We get 225 pi over 180. And if you do 225 over 180 and simplify that fraction, you're going to get 5 over 4. So in this case, we get 5 pi over 4 radians back. Okay, so to convert from degrees to radians, take your given degree measure, multiply by pi over 180. That gives you your equivalent, um, radian measure. And again, it works, it works for pi, 180 degrees too. Watch, if I do that times pi over 180 degrees, that completely cancels, and sure enough, yeah, pi and 180, same thing. Okay, now let's go the other way. Let's convert from radians into degrees. So instead of multiplying by pi radians over 180 degrees, we go the other direction. We multiply by 180 degrees over pi radians. Okay, so if we want to convert from radians to, take your radian measure, multiply by 180 degrees over pi radians. Your radian units cancel out, giving you back your degrees. Okay, so let's take a look. 5 pi over 6, I'm going to multiply by 180 degrees over pi radians. Pi's cancel out. That's usually the way I remember to multiply by this. I want those pi's to go away. Now I'm just going to use my calculator. I'm going to do 5 times 180 up top. Okay. And that ends up being 900 over the 6, divide by 6. And it looks like 5 pi over 6 is equivalent to 150 degrees. Okay, next up, 3 pi over 2, convert 2 degrees, multiply by 180 degrees over pi radians. Pi's are gone. 3 times 180 is 540, divided by 2 is 270 degrees. Okay, so down there at the bottom of the circle, 270 degrees is the same thing as 3 pi over 2. And in part C, pi's cancel. 3 times 180 is again 540. And divided by 4 this time is 135 degrees. Okay, so that's converting between the two. Now, we should also feel comfortable with the fact that radians do not always have to be in terms of pi. Although often they are, they're not always going to be in terms of pi. Convert each of the following radian angles, which aren't in terms of pi, into degrees. And by the way, up with these pendulum problems and clock problems, those were not in terms of pi either. Those were just angles that were not, those were radian angles, but were not in terms of pi. 2.6 radians, 0.55 radians. So they're not always in terms of pi, okay? But it's, look, to convert from radians to degrees, it's the same idea. We're going to take it, our given radian measure, we're going to multiply by 180 degrees over pi. So 5.8 times 180 degrees over pi. Now on your calculator, you're just going to do 5.8 times 180 divided by, and then use the pi symbol, which is second up arrow on the right hand side. It's right above the division key. Okay, so you can do 5 times 180 divided by pi. These are not always going to look very nice. You often get decimals back. They're saying to round to the nearest degree. I'm getting about 332 degrees back. 5.8 radians is the same as 332 degrees. Okay, let's see what 4.2 radians is the same as in degrees. So again, I'll multiply by 180 degrees over pi radians. 4.2 times 180 divided by pi on my calculator is about 241 degrees to the nearest degree. And in part C, let's go ahead and take negative 2.5 multiplied by 180 degrees over pi radians. Negative 2.5 times 180 divided by pi is about negative 143 degrees. Okay. And last but not least, an angle drawn in standard position whose radian measure is 2 radians would terminate in which of the following quadrants. Okay, so I would recommend, since we're much more comfortable with degrees, if we get a problem like this, let's convert to degrees. So 2 radians times 180 degrees over pi radians. Let's see, 2 times 180 divided by pi. That's going to be about 115 degrees, which will put us in quadrant 2. Okay, so pause, take some time to try the homework, and then take a look at the solutions if you need help, and see if you got them correct. Now for number 4, there wasn't one like this in the lesson, but what I'm doing here, let's take a look at these. Whoops. Let's take a look at these. All right. In part A, we want the reference angle for 2 pi over 3 radians. So what you notice I did, remember, 1 pi is over here and 2 pi is over here. So what I do is I look at the given denominator and I write 1 pi and 2 pi in terms of the common denominator. So 1 pi I could write as 3 pi over 3, and 2 pi I wrote as 6 pi over 3. So what that tells me then is, look, if this is 3 pi over 3, an angle at 2 pi over 3 is going to be a little before that in quadrant 2. Then what I do is I subtract, right? Here's my reference angle in pink. How far apart are they? Well, 3 pi over 3 minus 2 pi over 3. Common denominators, we can subtract the tops, leaves us with an angle of 1 pi over 3. In part B, right, we have a denominator of 6. So 1 pi is 6 pi over 6, 2 pi is 12 pi over 6. 11 pi over 6 is going to be a little short of 12 pi over 6. Okay, so again, in pink is my reference angle, and if I do 12 pi over 6 minus 11 pi over 6, we get 1 pi over 6 back for the reference angle. And in the last one, the denominator was 4, so there's 1 pi, there's 2 pi with a denominator of 4. 5 pi over 4 would be a little past 4 pi over 4, right? And my reference angle in pink, 5 pi over 4 minus the nearest x-axis, which is at 4 pi over 4, leave me with 1 pi over 4 for my reference angle. Okay? And then the applications were like the pendulum problems and clock problems. Okay, so take a look at these. And feel free to shoot me an emails if you have questions. Have a good day.